Example 16.6, internal resistance of a battery, is on page 597, and it sort of gets into the difference between EMF and change in voltage. And usually we associate them as being much the same. That's true as long as we ignore the fact that the battery does have its own resistance. In this case, we won't. The problem reads, you buy a 9-volt battery. To check whether it really produces a 9-volt potential difference across its terminals, you use a voltmeter and find that it reads 9 volts. Satisfied, you build this circuit shown in the figure. An ammeter, not shown, so the ammeter would measure current, indicates a 1.5 amp current through the 5.0 ohm resistor. I should probably draw in that current. A voltmeter reads 7.5 volts across the battery and negative 7.5 volts across the resistor. Two parts to this. A, explain why the measurements are unexpected. And B, what are the possible reasons for the discrepancy between the expected and the actual results? So here's our sketch of our circuit diagram. So the EMF of the battery, the squiggly looking E, is 9 volts. However, the potential difference across it is only 7.5 volts. Current through the resistor we measured with an ammeter to be 1.5 amps. But if we were to do Ohm's law of that to figure out what that current should be, it would look something like this, where current equals, and instead of saying change in voltage right now, let's say EMF over resistance. Well, our EMF was 9 volts, our resistance was 5 volts, 5 ohms, I should say. That would give us, in theory, a current of 1.8 amps, not 1.5. So this is what we would probably expect it to be. So I'm going to copy this diagram and show it to you in a different way. If we wanted to take a 1.8 amp current and slow it down to 1.5 amps, the way we would do that would be to increase the resistance or include another resistor. So you could either, since we know that there's only one resistor, imagine the battery has a little resistor in it. Does the battery actually have a little resistor? No, but the battery has its own internal resistance. So its own internal resistance we're going to represent with a lowercase r. That's the internal resistance of the battery, while our regular resistor is going to be a big R. So if we think of it with the loop rule that we did last time, we could say that the EMF and then going through this from the negative to positive, going downstream like we normally would, the voltage or the voltage difference would be negative IR. So in this case, negative I times little r. And we continue around, and the voltage difference here would be negative IR. But now we're going to call that big R. Those voltage drops have to be equal to 0. If we're interested in finding out what little r is, we should probably try to get little r by itself. So I'm going to add big I little r to both sides. These will cancel. We are then left with, ooh, I don't want that to be green at all. Silly. Our EMF, oh, that's little crazy with my squiggles, minus big I, little r, equals IR. But again, I want to get little r by itself by making little dots. So I'm going to divide by big I. Divide by big I. At this point, I'll cross that out. We have little r isolated. Now we can put in our actual numbers. Our EMF value was a positive 9.0 volts minus our current, our measured current, 1.5 amps. Our known resistor, 5.0 amps, or I'm sorry, 5.0 ohms over our current, 1.5 amps, our actual measured current. If we solve for R at this point, multiply and divide, we get the resistance to be equal to 1.0 ohms. So the battery has its own internal resistance of 1 ohm. To think of this, to kind of go back and say, well, would this be enough to do that? Think of it with Ohm's law. So current equals EMF over our total resistance. So let's say big R plus little r. Okay, well, current would have to be equal to 9 volts over 5 ohms plus 1 ohm. So 9 volts divided by 6 ohms is going to give us a current of 1.5 amps. So that solves the current mystery. As far as why does the voltage look so weird, we would expect it to be 9. It reads 7.5. Let's take this equation and bring it down here again and work with it a little bit. So EMF minus big I little r equals, well, I'm going to minus big I big R is equal to 0. Let's get big I little r by itself on the other side. And I'll show you why in the middle in a minute here. So I'm going to switch colors. Yeah, close enough. You're probably wondering, why is he only moving that? That will cancel. So we've got our EMF, our big I little r equals big I big R. The reason I did that is because this here, the EMF minus the voltage drop, is what we model as our battery. We've got our EMF value and voltage drop against that battery's internal resistance. So we're treating this battery as an EMF and an internal resistance. Usually we just say, don't worry about resistance, EMF is equal to voltage. Here we're saying resistance is actually there. Let's look at EMF and resistance separately. So if we're thinking about both of them, these two things together give us the voltage drop across the battery. So our voltage drop across the battery equals current times resistance. Our current, 1.5 amps, and our resistance of 5.0 ohms gives us a voltage drop across the battery of 7.5 amps. Or I'm sorry, not amps, volts. Volts, I say. Oh, why don't we just erase then? So that explains why we get some weird readings. A lot of times we will think in theory batteries have no resistance. In practice, they do, though it's usually very, very small. And You don't really notice battery resistance at all until you start using resistors with very little resistance. If this was a resistance, had resistance in the hundreds of ohms, then we can pretty much assume that the battery doesn't have resistance. But when we start using very little resistors, then any resistance that slows down that flow becomes pretty significant. So if we have a very small resistor, we can't say that EMF and change in voltage is the same thing. However, if our resistors or our resistance is much, much bigger than the internal resistance of the battery, like I'm saying in the hundreds or thousands of ohms, then we can say that the change in voltage of the battery is pretty much equal to EMF.